Before the 20th century, physics appeared nearly complete. By the late 1800s, scientists believed they had uncovered the fundamental laws governing nature. Motion, heat, sound, electricity, magnetism, and light all seemed explainable using a unified framework, classical physics. At its core were three pillars: Newtonian mechanics, governing motion and forces; thermodynamics, governing heat, energy, and equilibrium; and Maxwell's electromagnetism, governing light and radiation. Together, these laws describe the universe as continuous, not discrete; deterministic, not probabilistic; smooth and predictable. There was great confidence. In 1894, physicist Albert A. Michelson famously remarked that the future of physics involved only measuring constants to more decimal places. The laws themselves, he believed, were already known. This confidence would soon collapse. Every object with a temperature above absolute zero emits radiation. This phenomenon is called thermal radiation. A hot iron glows red. A stove emits infrared radiation. The sun emits visible light. These emissions do not depend on the object's shape or composition alone, but primarily on its temperature. Physicists wanted to answer a deceptively simple question: how much energy does a hot object emit at each wavelength of light? This question would become the doorway to disaster. To study thermal radiation cleanly, physicists introduced an ideal system: the blackbody. A blackbody is an object that absorbs all incoming radiation, emits radiation only based on temperature, independent of material or surface texture. In practice, scientists approximated blackbodies using hollow cavities with a tiny hole. Radiation entering the hole gets absorbed after many reflections. Radiation escaping the hole represents pure thermal emission. This setup was experimentally achievable and, crucially, measurable. By the mid to late 19th century, experimentalists had measured blackbody radiation spectra. They plotted wavelength, x-axis, intensity of radiation, y-axis. What they found was remarkably consistent. At long wavelengths, infrared, low intensity; at intermediate wavelengths, a clear peak; at short wavelengths, ultraviolet, intensity drops rapidly. This smooth curve was known as the blackbody spectrum. The problem was not experimental uncertainty. The data was solid. The problem was theory. Physicists attempted to derive the blackbody spectrum using known laws. They relied on equipartition theorem from statistical mechanics, classical electromagnetism, and continuity of energy. The equipartition theorem stated every independent mode of motion in a system at thermal equilibrium carries an average energy of kT. This principle worked extremely well for gases and solids, so physicists applied it to electromagnetic radiation inside a cavity. This seemed reasonable. It was a fatal mistake. In 1900, Lord Rayleigh, John William Strutt, one of Britain's most respected physicists, attempted to derive the blackbody spectrum. Rayleigh treated electromagnetic radiation as standing waves inside a cavity, each wave mode behaving like a harmonic oscillator. Using classical assumptions, he calculated the number of wave modes per wavelength, the energy each mode should carry via equipartition. The result was elegant. It was also catastrophically wrong. Rayleigh's work was refined by James Jeans, leading to the Rayleigh-Jeans law. This formula predicted good agreement at long wavelengths, rapidly increasing intensity as wavelength decreases. As wavelength approaches zero, ultraviolet, the predicted energy approaches infinity. This implied any warm object should emit infinite energy, and the universe should instantly vaporize. This absurd result became known as the Ultraviolet Catastrophe. This was not a small error. It was not a missing correction factor. The catastrophe arose from deep assumptions. Energy is continuous. Oscillators can store unlimited energy, and all modes are equally accessible. No adjustment within classical physics could fix this. The theory worked perfectly at low frequencies and failed completely at high frequencies. This partial success made the failure even more disturbing. Experimentalists such as Lummer and Pringsheim and Rubens and Kurlbaum produced increasingly precise blackbody measurements. Their data showed clear deviation from Rayleigh-Jeans at short wavelengths, a sharp cutoff in ultraviolet radiation. Nature was not diverging.
only theory was. By 1900, physicists were uneasy. They had reliable experiments, trusted mathematics, a theory predicting nonsense. This was not merely an error, it was a conceptual breakdown. As historian of science Thomas Kuhn would later describe it, this was a crisis, not a puzzle. Max Planck was not a revolutionary by temperament. He was conservative, deeply committed to classical thermodynamics, skeptical of statistical interpretations. Planck initially believed the second law of thermodynamics was absolute, not probabilistic. Ironically, it was this belief that pushed him toward a radical idea. Planck studied energy exchange between matter and radiation. He modeled matter as microscopic oscillators or resonators interacting with electromagnetic radiation. At first, he tried every classical trick. All failed. Then, in October 1900, Planck made a mathematical move he himself described as an act of desperation. Planck assumed energy could only be emitted or absorbed in discrete packets. He proposed E equals h nu, where E is energy, nu is frequency, h is a new constant, now called Planck's constant. This assumption violated classical continuity, had no physical justification at the time, was introduced purely to fit data. But it worked perfectly. Planck derived a new formula that matched experimental data at all wavelengths, reduced to Rayleigh genes at low frequencies, suppressed ultraviolet divergence naturally. The ultraviolet catastrophe vanished. Physics had crossed a boundary. Planck did not immediately believe energy was truly quantized. He viewed quantization as a mathematical trick, a temporary assumption. It would take others, Einstein, Bohr, and later Schrödinger and Heisenberg, to realize its true meaning. References: Planck.M.1901 on the law of distribution of energy in the normal spectrum, Annals of Physics. Rayleigh.Lord.1900 remarks upon the law of complete radiation, Philosophical Magazine. Jeans.J.1905 on the partition of energy between matter and ether, Philosophical Magazine. In 1905, a 26-year-old patent clerk named Albert Einstein published a series of papers that would permanently alter physics. One of them directly addressed the meaning of Planck's quantum hypothesis. Unlike Planck, Einstein did something radical. He treated energy quantization as physically real, not just a mathematical trick. This move would transform the ultraviolet catastrophe into a new ontology of nature. Einstein analyzed an experimental phenomenon known since the 1880s, the photoelectric effect. When light shines on certain metals, electrons are ejected from the surface, but only if the light exceeds a minimum frequency. Increasing intensity does not eject electrons below this threshold. Classical wave theory predicted energy should depend on intensity, not frequency. Any frequency should work if intensity is high enough. Experiments disagreed. Einstein proposed light consists of discrete quanta, later called photons. Each photon carries energy E equals h nu. An electron is ejected only if one photon has sufficient energy. This explanation confirmed Planck's constant as a real physical quantity and demonstrated that quantization applies to light itself. Einstein would later receive the 1921 Nobel Prize not for relativity, but for this work.
The ultraviolet catastrophe and the photoelectric effect share the same root problem. Classical physics assumes energy can be divided arbitrarily. Quantum physics denies this. At high frequencies, energy packets are large. High-frequency modes are difficult to excite. Ultraviolet radiation is naturally suppressed. This suppression is not imposed, it emerges. The catastrophe disappears because nature refuses to populate infinite high-frequency modes. Einstein's proposal was deeply unsettling. It implied light behaves as both wave and particle. Energy exchange is discrete. Classical continuity is broken at a fundamental level. Many physicists resisted this idea for decades. Even Planck himself was uncomfortable. The equipartition theorem had been one of classical physics's greatest successes. It worked for translational motion, rotational motion, vibrational modes at low frequencies. But blackbody radiation exposed its limitation. Equipartition assumes all degrees of freedom are equally accessible. energy can be shared continuously. Quantum theory introduces restricted accessibility. High-frequency oscillators require energy packets too large to be thermally available. Thus, high-frequency modes freeze out. Equipartition fails. This failure is not accidental, it is fundamental. Einstein applied quantum ideas to another classical failure, specific heat. Classical theory predicted specific heat of solids should be constant. Experiments showed specific heat drops sharply at low temperatures. Einstein modeled atoms as quantum oscillators. Result: excellent agreement with experiment. Further confirmation of quantization. The ultraviolet catastrophe was not alone. Classical physics was failing everywhere high frequencies or low temperatures appeared. In 1912, Peter Debye refined Einstein's model by treating vibrations as collective modes and introducing a maximum frequency cutoff. Debye's theory fully explained low-temperature behavior and reinforced the idea that nature limits accessible modes. Once again, infinity vanished. In 1913, Niels Bohr applied quantization to atoms. He proposed electrons occupy discrete orbits. Energy transitions emit or absorb quanta. This explained hydrogen spectral lines and atomic stability. Although Bohr's model was incomplete, it demonstrated quantization governs matter, not just radiation. Classical electrodynamics predicted orbiting electrons should radiate energy and atoms should collapse in microseconds. They do not. Quantization prevents collapse. The same principle that solved the ultraviolet catastrophe keeps matter stable. By the mid-1920s, Heisenberg introduced matrix mechanics. Schrödinger introduced wave mechanics. Born introduced probability interpretation. Quantum mechanics replaced classical mechanics at small scales. Continuity gave way to discreteness. Determinism gave way to probability. In modern terms, the ultraviolet catastrophe teaches us classical theories overcount degrees of freedom. Nature imposes quantum constraints. Infinite predictions signal conceptual error. This lesson extends beyond blackbody radiation. From a modern perspective, the ultraviolet catastrophe was not really about light. It was about counting states. Classical physics assumed an infinite number of electromagnetic modes, each mode equally accessible at thermal equilibrium. No restriction on energy sharing. Mathematically, the catastrophe arises from the density of states growing rapidly with frequency. In 3 dimensions, g of v proportional to nu squared. As frequency increases, the number of available modes explodes. Classical theory assigns each mode an average energy kT. This combination guarantees divergence. The catastrophe was inevitable, not accidental. Quantum theory modifies one assumption only: energy exchange is discrete. This single constraint limits accessibility of high-frequency modes, suppresses occupation numbers exponentially. Planck's law introduces the factor 1 over e to the h nu over kt minus 1. At high frequencies, the exponential term dominates. Occupation probability collapses. Infinity disappears because nature refuses to populate high-energy states freely. In 1924, Satyendra Nath Bose re-derived Planck's law using a radically new counting method. Bose treated photons as indistinguishable particles, obeying new statistical rules. Einstein immediately recognized the importance. This approach eliminated classical equipartition, naturally produced Planck's distribution, and introduced quantum statistics. Blackbody radiation became the first manifestation of quantum field behavior. In modern physics, radiation is described as a quantized electromagnetic field. Each mode is a quantum harmonic oscillator. Energy levels are discrete. The energy equals n plus 1/2 times h nu. Thermal radiation emerges from population of field modes, governed by Bose-Einstein distribution. The ultraviolet catastrophe never appears because zero-point energy does not contribute thermally. High-frequency excitations are exponentially suppressed. Quantum field theory reveals something unsettling. Even at absolute zero, fields still fluctuate.
Each mode carries the energy equals 1/2 times h nu. This zero-point energy exists even in vacuum. Curiously, zero-point energy does not cause an ultraviolet catastrophe. It is present but not thermally accessible. This distinction is subtle and profound. Zero-point energy is not exchangeable with matter at equilibrium. It does not contribute to blackbody radiation. Thermal radiation depends on excited states, occupation numbers. Thus, the catastrophe is avoided not by removing infinity, but by restricting interaction. This foreshadows deeper issues in modern physics. In quantum field theory, infinities still appear, but in controlled, systematic ways. Renormalization absorbs infinities into measurable parameters, preserves predictive power. The ultraviolet catastrophe was an unrenormalized infinity, a warning sign that the theory itself was incomplete. Modern physics learned how to recognize such signals. The phrase ultraviolet catastrophe has become symbolic. Similar problems appear in quantum electrodynamics, self-energy divergences, quantum gravity, non-renormalizability, vacuum energy, cosmological constant problem. In each case, high-energy behavior reveals theoretical limits. New physics is required. The original catastrophe taught physicists how to recognize when conceptual revision is unavoidable. Modern physics accepts all theories have domains of validity. Classical physics is an effective theory. It fails at high frequencies and small scales. Cutoffs are no longer viewed as ad hoc. They signal where new degrees of freedom emerge, where new principles apply. The ultraviolet catastrophe was the first explicit demonstration of this principle. From today's perspective, classical electrodynamics is not wrong, it is incomplete. It emerges as a statistical average, a low-frequency limit, a macroscopic approximation. Planck's law reduces to Rayleigh genes naturally when h nu is less than kT. Classical physics survives, but only in its proper domain.
Before 1900, physics assumed space, time, energy were infinitely divisible. The ultraviolet catastrophe forced a revision. Nature has grain. Continuity is approximate, not fundamental. This was not merely technical. It altered ontology, epistemology, scientific realism. Planck's constant sets a scale. Below it, classical intuition fails. Above it, continuity emerges. It is not just a number, it is a boundary between descriptions. Much like speed of light limits velocities, Boltzmann's constant links temperature to energy. Classical physics extrapolated success at low energies into regimes where assumptions no longer held. The ultraviolet catastrophe teaches success does not guarantee universality. This lesson reappears throughout modern science. References: Bose, 1924, Planck's law and the hypothesis of light quanta; Einstein, 1925, quantum theory of the monatomic ideal gas; Mandel and Shaw, quantum field theory. At the deepest technical level, the ultraviolet catastrophe arose from a misuse of phase space. Classical statistical mechanics assumes phase space is continuous. States can be occupied arbitrarily closely. No fundamental minimum cell exists. When electromagnetic radiation is treated classically, each field mode corresponds to a harmonic oscillator. Each oscillator contributes kT of energy. The number of modes grows without bound. Mathematically, the integral over phase space diverges. This divergence is not an error in calculation, it is an error in ontology. Quantum mechanics introduces a profound modification. Phase space is not continuous, it is grainy. Each quantum state occupies a minimum cell of size delta x delta p equals h. For fields, this translates into discrete occupation numbers, restricted state counting. Planck's constant acts as a regulator preventing infinite state density. The ultraviolet catastrophe disappears because you cannot pack infinite states into finite phase space. High-frequency modes require prohibitively large quanta. No classical correction could fix the catastrophe because classical theory has no natural scale. There is nothing to limit arbitrarily small wavelengths. Quantum theory introduces a scale. This is the deepest reason classical physics failed. It lacked a principle to limit resolution. Blackbody radiation is not just about energy, it is about entropy maximization. Thermal equilibrium corresponds to maximum entropy, subject to conserved quantities. Classical entropy calculation overcounts microstates, assigns equal weight to all modes. This produces infinite entropy at high frequencies. Quantum entropy counts discrete microstates, naturally suppresses improbable configurations. The ultraviolet catastrophe was an entropy explosion. Planck's original derivation relied on combinatorial counting, discrete energy elements. He calculated the number of ways energy quanta could be distributed subject to fixed total energy. Maximizing entropy under these constraints yields Planck's distribution. In modern terms, the ultraviolet catastrophe disappears because high-frequency disorder is entropically unfavorable. From an information perspective, each photon carries information. High-frequency photons carry more energy per bit. Thermal systems prefer many low-energy quanta, fewer high-energy quanta. Nature optimizes information storage efficiency. This anticipates modern connections between thermodynamics, information theory, and quantum mechanics.
In quantum field theory, temperature is introduced via Wick rotation, imaginary or Euclidean time. Time becomes periodic, tau equals h bar over kt. This periodicity imposes boundary conditions, discretizes allowed frequencies, Matsubara modes. The ultraviolet catastrophe is avoided because high-frequency modes are exponentially suppressed. Thermal fields cannot excite arbitrarily short timescales. Temperature itself becomes a quantization constraint. The radiation field's behavior is encoded in a partition function, z equals pi over k, 1 over 1 minus e to the minus beta h nu k. Each mode contributes independently. This formalism makes divergence conditions explicit, shows why classical limits fail, demonstrates how quantization controls infinities. The catastrophe appears only if h goes to 0. Classical physics corresponds to an unphysical limit. Taking h goes to 0 is not smooth. This is a crucial lesson. Limits do not commute in physics. High-frequency limits and classical limits conflict. The ultraviolet catastrophe arises from taking limits in the wrong order. The most perfect blackbody spectrum ever observed is not in a laboratory. It is the cosmic microwave background, CMB, measured by COBE, WMAP, and Planck satellite. The CMB follows Planck's law with astonishing precision. This confirms quantum theory at cosmological scales, thermal equilibrium in the early universe. If classical physics governed the early universe, radiation energy density would diverge, expansion would be impossible, structure formation would fail. Quantum mechanics is not optional in cosmology. The ultraviolet catastrophe would have destroyed the universe before it began. As the universe expands, wavelengths stretch, high-frequency modes redshift, thermal populations evolve. Quantum field theory in curved spacetime explains why radiation cools, why blackbody shape persists, why catastrophe never reappears. Quantum field theory reintroduces ultraviolet issues, self-energy divergences, vacuum fluctuations, infinite loop corrections, but now infinities are classified, controlled by renormalization, linked to measurable parameters. The catastrophe taught physicists how to manage such problems. In quantum gravity, no consistent ultraviolet completion yet exists. Spacetime itself may be discrete. The Planck scale replaces the Planck constant as a regulator. The lesson of the ultraviolet catastrophe echoes again. When infinities appear, reality is telling us something is missing. References: Huang, K., Statistical Mechanics, Pathria and Beal, Statistical Mechanics, Zinn-Justin, Quantum Field Theory and Critical Phenomena, Weinberg, S., Cosmology.
One of the deepest lessons drawn, retroactively, from the ultraviolet catastrophe is this: physics is not scale-free. Classical physics implicitly assumed the same laws apply at all wavelengths. No privileged scale exists. Zooming in never changes the rules. Quantum theory disproves this. The failure of classical radiation theory was a failure to recognize that new behavior emerges at small scales. Modern physics understands ultraviolet problems through the renormalization group, RG. The RG describes how physical laws change with scale, how coupling constants flow as frequency increases, why certain theories break down at high energy. From this perspective, Rayleigh-Jeans theory is a low-energy effective theory. It must fail when extrapolated beyond its validity. The ultraviolet catastrophe is the first historical example of an RG failure before RG existed. At low frequencies, classical electromagnetism is an excellent approximation. Quantum corrections are negligible. At high frequencies, quantum behavior dominates. Classical variables lose meaning. These regimes correspond to different fixed points in theory space. The catastrophe emerged because physicists tried to extend one fixed point into another regime where it did not apply. Classical theory treats modes as independent. Quantum theory reveals modes are entangled. Field correlations exist even in vacuum. Thermal radiation is not merely random emission. Entanglement constrains how energy distributes, how information propagates, how entropy grows. The ultraviolet catastrophe ignored correlation structure. Entanglement entropy typically scales with surface area, is sensitive to high-frequency modes. In quantum field theory, entanglement entropy diverges without a cutoff. A fundamental length scale is required. This mirrors the original catastrophe. Infinite modes equals infinite entropy. Cutoffs restore meaning. Once again, ultraviolet infinities signal incomplete description. Thermal radiation can be understood as continuous interaction between matter and field, rapid decoherence of phase information, emergence of classical behavior from quantum substrate. High-frequency modes decohere poorly. They remain weakly populated. This dynamical suppression complements statistical suppression. In the 1970s, Stephen Hawking showed that black holes emit radiation. This radiation has a black body spectrum, depends only on surface gravity, and is inherently quantum. A black hole is the most perfect black body imaginable. Near a black hole horizon, frequencies blue shift dramatically. Trans-Planckian modes appear. Classically, this leads to divergence, infinite energy densities. Quantum field theory regulates these effects and prevents catastrophe, but raises new conceptual puzzles. The ultraviolet catastrophe reappears, now in curved spacetime. Hawking radiation depends on modes that originate at arbitrarily high frequencies, lie beyond known physics. This is a modern echo of the original catastrophe. Are we extrapolating too far again? Quantum gravity is expected to resolve this, but has not yet done so. An accelerating observer perceives vacuum as a thermal bath, temperature proportional to acceleration. This phenomenon shows temperature is observer-dependent. Thermal radiation is not absolute. Mode occupation depends on reference frame. The ultraviolet catastrophe assumes a universal observer. Quantum field theory denies this. In curved spacetime, horizons impose natural cutoffs. Mode accessibility is restricted. Infinite frequencies lose operational meaning. Geometry becomes a regulator. This suggests the ultimate cure to ultraviolet catastrophes may be geometric, not algebraic. Modern physics increasingly emphasizes what can be measured, what interactions are possible, what information can be extracted. Infinite energy densities cannot be operationally accessed. Signal breakdown of description, not reality. The ultraviolet catastrophe taught physicists to distrust mathematical infinity without physical access. From the catastrophe onward, physicists learned to ask, where does this theory apply? What assumptions fail at extreme scales? What quantities remain observable? These questions now guide quantum gravity, high-energy particle physics, cosmology. Classical physics assumed short wavelengths affect only short-scale behavior.
Large-scale physics is independent of microscopic details. Quantum field theory overturned this. In many systems, ultraviolet, high-energy behavior influences infrared, large-scale structure. Small-scale assumptions echo into macroscopic predictions. The ultraviolet catastrophe was the first warning that this separation fails. In quantum field theory and string theory, one encounters UV-IR mixing. Regulating high-frequency modes alters low-frequency physics. Cutoffs introduce new long-distance effects. Blackbody radiation already hinted at this. Removing ultraviolet divergences reshapes the entire spectrum. The peak position, Wien's law, depends on Planck's constant. Thus, ultraviolet physics determines where the energy actually appears. Modern theories increasingly suggest nature may encode high-energy information in low-energy observables. The catastrophe showed that you cannot freely discard short-wavelength behavior. Ignoring it breaks the theory entirely. The holographic principle proposes the maximum information inside a region scales with its surface area, not with its volume. This directly contradicts classical intuition. Classical field theory predicts infinite degrees of freedom per volume, leading inevitably to ultraviolet divergences. Holography enforces a finite number of physical states, a fundamental ultraviolet cutoff encoded geometrically. In a holographic framework, radiation modes are not independent bulk degrees of freedom. They are emergent descriptions of boundary data. This implies mode counting must saturate. Infinite ultraviolet states are unphysical abstractions. The ultraviolet catastrophe vanishes not because energy is discretized, but because the notion of independent modes breaks down. In anti-de Sitter and conformal field theory correspondence, thermal radiation in the bulk corresponds to thermal states on a boundary. Ultraviolet behavior in one description maps to infrared behavior in the other. Thus, catastrophic divergence in one frame becomes controlled behavior in the other. The catastrophe becomes coordinate-dependent, not absolute. Jacob Bekenstein proposed a limit. There is a maximum entropy that can be stored in a finite region. This bound prevents infinite information density, infinite energy density. Classical blackbody theory violates this bound. Quantum physics enforces it naturally. If classical theory were correct, arbitrarily small volumes could store infinite thermal energy. Quantum bounds forbid this. There exists a maximum entropy per area, a maximum temperature before gravitational collapse. The ultraviolet catastrophe is incompatible with gravity. Gravity introduces horizons, collapse, finite information capacity. Thus, even if quantum mechanics did not regulate the ultraviolet, gravity would. The catastrophe disappears again, this time through space-time itself. Modern approaches suggest radiation is not fundamental. Fields are effective descriptions. Space-time geometry may emerge from entanglement. If this is true, ultraviolet modes are bookkeeping artifacts. Physical reality contains far fewer degrees of freedom. The ultraviolet catastrophe arose from mistaking reality for description. In ADS/CFT, space-time distance emerges from entanglement entropy. Cutting off high-frequency modes changes geometry itself. This implies ultraviolet physics shapes space-time. Catastrophes are geometric inconsistencies. The concept of independent Fourier modes may be a low-energy convenience, not a fundamental truth. Blackbody radiation works because modes of approximate reality at accessible scales fail catastrophically when extrapolated beyond them. The ultraviolet catastrophe did more than break an equation, force a correction. It forced physicists to confront the limits of reductionism, the dangers of infinite extrapolation, the non-universality of successful theories. Every major theoretical revolution has followed the same structure: a successful theory, extrapolation beyond its domain, divergence or paradox, introduction of a new principle. The ultraviolet catastrophe was the template. Even now, we do not know the ultimate ultraviolet completion of physics. We do not know whether space-time is continuous. We do not know whether quantum mechanics itself is final. The catastrophe is not resolved, it is transformed. References: Susskind, The World as a Hologram. Maldacena, 1997, The Large N Limit of Superconformal Field Theories. By now, a clear pattern has emerged. Every time physics predicts infinite energy, infinite density, infinite information, it later turns out that the theory was extrapolated beyond its domain. A deeper principle was missing. The ultraviolet catastrophe was the first explicit warning that infinity is not a physical prediction, but a diagnostic. Modern physics increasingly treats infinities as signs of incomplete description, markers of missing structure, invitations to deeper theory. From Planck's hypothesis onward, nature has repeatedly revealed a preference for finiteness. Quantized energy levels, finite entropy bounds, discrete charge, minimal length scales, Planck's length. Each of these restricts infinite divisibility, prevents ultraviolet divergence, and preserves physical meaning. The ultraviolet catastrophe forced physics to abandon the idea that continuity is sacred. Quantum theory resolved the catastrophe, but not all ultraviolet problems. Open questions remain. Does space-time have a smallest unit? Is Planck's constant fundamental or emergent? Will quantum gravity introduce new discreteness? The catastrophe teaches humility. Even our most successful theories may be approximations. Unlike ordinary errors, the ultraviolet catastrophe could not be patched, could not be ignored, could not be reinterpreted away. It demanded a conceptual leap. This makes it one of the most productive failures in science. Without it, quantum mechanics may have been delayed by decades. Atomic physics would remain mysterious. Modern technology would not exist. After 1900, physics changed its method. Before, assume continuity, apply mathematics universally, trust extrapolation. After, question assumptions, respect scale limits, treat infinities as warnings. This methodological shift is one of the catastrophe's lasting legacies. What began as a problem about glowing objects reached into atoms, reshaped thermodynamics, altered our view of light, challenged the nature of reality. Few problems in science have had such reach. Modern physics still faces ultraviolet crises, vacuum energy, quantum gravity, information paradoxes. Each resembles the original catastrophe in structure: a trusted theory, an infinite prediction, and a conceptual impasse. The lesson remains active. From the ultraviolet catastrophe, physicists learned a quiet rule. When mathematics predicts infinity, ask what assumption you forgot to question. This rule guides theory development, experimental interpretation, and scientific restraint. The catastrophe speaks to a broader human lesson. Success can hide fragility. Precision does not guarantee truth. Deeper understanding often begins with failure. This is why the story endures. We began with a simple problem. How does a hot object radiate energy? Classical physics answered confidently and incorrectly. Nature responded not with correction, but with refusal. The universe did not radiate infinite energy. Instead, it revealed a boundary. That boundary was quantum. It was not a catastrophe of nature, but a catastrophe of assumptions. Nature behaved sensibly. Our ideas did not. In place of classical certainty came quantization, probability, limits, structure. Physics did not collapse, it matured. The ultraviolet catastrophe marks the moment when physics learned something essential. Reality is not obligated to follow our intuitions. Light is not infinitely divisible. Energy is not continuous. Nature is economical, structured, and finite where theory once demanded infinity. From a glowing cavity emerged a revolution. From a failed prediction emerged a deeper truth. And from that truth, modern physics began. Final references: Planck, Scientific Autobiography; Heisenberg, Physics and Philosophy; Feynman, The Character of Physical Law; Smolin, 3 Roads to Quantum Gravity; Z, Fearful Symmetry.